All right, so in this video, we're going to talk about radian measure. And for those of you that are going on to calculus, this is going to be far more important than degree measure, and it's probably something new for most people. So to discuss radian measure, we're actually going to start off with the unit circle. A little while ago, I told you that even though we're studying trig, everything's going to come from the idea of a circle. So the unit circle is a circle centered at 0, 0 with a radius of 1. So the equation for this would be x squared plus y squared equals 1. So if I draw the unit circle, I'll have a picture that looks something like that. And I'll go ahead now and I'll create an angle in standard position. So maybe I'll take that terminal side out just like that. This would be angle theta, swept out in the counterclockwise direction, denoting a positive measure. And this intercepted arc right here, we're going to call S. And what we can come to the conclusion is that the measure of theta is actually equal to S radians. Okay, the measure of angle S the measure of angle theta equals S radians. So that's a really powerful statement for many reasons. But a couple things to keep in mind is that a radian, by looking at our picture, is just an arc length. So arc length is very, very important in trig. Another thing to remember is that arc length is just a real number. So a radian is just a real number. It's not relative to anything, unlike degrees are. So the radian is incredibly important. We'll use it far more often than we do the degrees. So hopefully you'll have a good understanding of it by the time we get finished with this section. And as for the conversion factor, pi radians is actually equal to 180 degrees, which means that over here on our unit circle, 180 degrees is equal to pi radians. So that's going to be where pi is. Now, before I actually go into any more detail on showing you how these things look, what I'd like to do is work the next few examples and instead show you how many degrees are in 1 radian and how many radians are in 1 degree. It's always something that's interesting to see, since degrees are something you're so used to seeing and visualizing, and radians probably aren't. Okay, so to run these calculations is actually pretty easy. Another unit conversion. If we have 1 radian, I'll want to go ahead and multiply by the unit conversion with a radian on bottom, a degree on top. You can see the radians go away, and whatever my answer is, I'm left with degrees. We would have 180 degrees in pi radians. So really, if I just take 180 divided by pi, that's going to give me approximately 57.3 degrees. So 1 radian is approximately 57 degrees. Now, in example 4, it's pretty similar. Our unit conversion would need to have a degree on bottom. And you can see, again, degrees go away and leave us with radians for our final unit. We know that there are pi radians per every 180 degrees. So pi divided by 180 would give us 0.0175 radians. So 1 degree is about 0.02 radians. So that might help you a little bit visualize. One other thing that I want to mention is hopefully throughout the notes you've been consistent in putting the degree symbol on all of your degree measurements. For radians, since they're real numbers, you can write RAD behind the number if you want to, or if you just leave it alone without units, because radians are real numbers, it's implied that in context of angular measure, the real number is just a radian. So you don't technically have to write anything in terms of units, unlike that of degrees. All right, so the final thing we'll talk about in terms of angles and their measurements would be arc length and area of a sector. So to start arc length, I'm just going to draw a pretty common picture that you've seen. Now it is a circle, and it is not necessarily the unit circle, so I'm just going to call the radius here, I'm going to call this r. And then if I extend out, we would have an angle theta, and we could also then have an arc length s. Now to come up with a formula for arc length, we're going to actually set up a proportion. So the first thing that I'm going to do is construct a ratio of the entire arc length of a circle over the angular measure needed for it. So the entire arc length of a circle is actually just going to be the circumference. So 2 pi r. And the angular measure to create an entire circle would be 2 pi. Now, proportionally, I'm going to now look at just the arc length we care about, s. The angular measure needed to create s in our picture is just theta. Now, cleaning this up, it's actually pretty convenient. We find out that r equals s over theta, and s being arc length, what we're looking for is just r times theta. R is the radius, and theta must be in radians. So that's always something you always want to look for. Make sure theta is in radians. Now, earlier I said this was not necessarily the unit circle, but you can see that if r was equal to 1, then your s would just equal theta. So the measure of angle theta would just be s radians, which is the arc length. Okay, so it all ties together nicely. In terms of area of a sector, for area of a sector, we'll do something pretty similar. A sector is just a kind of a wedge of the circle, or a slice of pizza, if you will. So the area would be that thing. So I'll go ahead and label it. Once again, we have r, we have theta, and then this whole thing here, that would be our s. And proportionally, again, we'll talk now about the entire circle. The area of the entire circle would be a pi r squared. The angular measure needed to create the entire circle would be a 2 pi. Now, for us, the area of the sector we'll call A, and the angular measure needed to create that sector would be theta. So similar to the last one, it doesn't divide off as nicely, but you can see when we do this, we get a 1/2 r squared equals a over theta, and our area now can be defined as 1/2 r squared theta. Again, the r is the radius, and the theta is required to be in radians.